Hello everyone, I am Peter from Ecxsight, and in this video I would like to talk about digital image correlation, about how we use it in engineering testing together with our devices such as Versatile One and more specifically designed loop or rod. Okay, so let's take a look. So in the beginning, please let me quickly tell you who actually Ecxsight is. We are a Czech company located in the beautiful town of Brno, developing a computer vision systems with focus on digital image correlation, specifically for systems in industrial testing. And our main target is to make DIC systems easy to use. So as a first thing, let's say we are not using a color but monochromatic cameras. And in this grayscale picture, we pick one point that we would like to track in time. This point is then searched in another image and in another image and always compared to the first image that we call a reference image. But we cannot pick only one point because it will be just one pixel, one level of gray. And this level of gray will be found numerous times in the whole image. We have to pick some bigger area, so typically something about 31 to 31 up to, let's say, 60 by 60 pixels. And this area creates a matrix of gray levels. And this area is more unique, more well specified, and this is then searched in the time. So let's describe the information we are working with. What we see, a human eye, is just a dark cross on a light background, but in the memory of the PC it's just the digits. So the dark ones have a lower value and the light ones have higher value. So here we specified an 8 by 8 pixel matrix that we would like to track, and we call this region a correlation template. And as you can see, the whole image moved 1 pixel vertically and 1 pixel horizontally. So hooray! We just tracked 1 pixel movement. But digital image correlation can do much better than that. And that is because digital image correlation does not use just black or white. So we use the whole grayscale. So if you are talking 8-bit depth, then we have values from 0 to 255. So if the tracked object moves just a part of the pixel, the edges just get not that well defined, but never mind, we can still use this information because we are using an interpolation of higher polynomials like cubic or B-spline to get the highest possible match with the reference image. And with use of this interpolation, the resolution of the DIC system can get way below 1 pixel. And if we consider the noise of current industrial cameras, we are talking something about 0.01 pixel. Now let's take a look at types of transformation we get in 2D for a planar deformation. We get actually 6 degrees of freedom. So it's 2 translations, X and Y. We get X and Y scale, then we have a shear and also rotation. And all this transformation we need to consider during the computation. And to describe this transformation we need some kind of contrast in the image. So let's get back in time now a little bit into the days where video extensometers used mark tracking, so they were looking for some specific mark. So we take a dot, we can see it describes both translations, X and Y, but it cannot describe a rotation. A single line can describe rotation and a vertical movement, but also it can slide on the line from side to side without knowing what exactly position it was or is the correct one. Then we got a cross, which seems to be fine because it describes rotations and both translations, but the best for DIC is something that we call a speckle pattern. It's a stochastic, random and unique matrix of gray levels that you can see all the way on the right. So in the top right corner you can see how the optimal stochastic high contrast speckle pattern looks like. And below it you see how it should not look like. It should not be a low contrast, it should not be isotropic, so the lines cannot, or the points cannot slide on the lines, and also it should not be repetitive, because then the algorithm cannot really tell which exactly symbol you are tracking, so it will jump from side to side. We will just lose your mark because the algorithm just would not have the confidence to determine the correct position. Although the conventional extensometers proved their functionality by years in practice, they simply reached their limits, and today's laboratories are looking for more and more information from each test, and this is where optical methods comes in handy for their advanced features, like neck detection, where we can minimize the risk of losing the necking area. So if you look at the image, the red arrow is marking the necking area, and of course if you have a conventional extensometer you will just lose the neck, and that will end up as an invalid test. And because DIC is a non-contacting method, there is no risk of damaging the device during the rupture of the specimen due to the released energy, so we can measure all the way up to the breakage. Also, measurements in environmental chambers or even furnaces are possible with proper setup and some optical filters. The most common use of our DIC-based video extensometer is a uniaxial tensile test. And you can notice that we applied more virtual probes than just a single line. So let's stop it here for a while. Did you notice the green line jumping from side to side? That's one of the advanced features I mentioned earlier. This probe we call an extreme line, and it behaves like multiple extensometers hanging on a single specimen. It gives you an average value from all possible gauge lengths during the elastic part, while performing a neck detection at the end of the test. This brings smooth reading and also minimizes the risk of missing the necking area. This feature is highly beneficial on long prismatic samples such as rebars, where you have quite short gauge length on a long sample length. This chart demonstrates both benefits of extreme line. On the left, the red line shows what happens when you miss the area of necking, and on the right side, you can see the comparison between single line and extreme line. A similar neck detection feature can be used also for transversal measurement, like here on a transversal line. It uses a multiple position measurement to give you an average from all cross-section lines or a value from the narrowest or widest cross-section. Another line-based probe is a bend line. It is designed for bending tests where it can give us not only the value of the maximal deflection, but also a strain value following the curvature of the sample. Torsion line is a unique feature of X-Sight's company that allows you to get an angular twist on a rounded specimen in 2D from a self-aligning probe. Alright, so that were line-based probes, but the true value of DIC is a possibility to obtain a strain mapping similar to finite element methods, and not unlike FEM, it uses a computational mesh with selectable triangulation type. You can also choose what type of tensor you would like to get. The results are then presented in a colorful map of deflection or strain. So let's take a look at the procedure of post-processing. I will create a new area, adjust it as I need, select Free Edit and also show the mesh. Now I can insert my user-defined points for an application where I cannot generate points over the whole specimen. It's, for example, a structure walls or some wings of an airplane, for example, that I can only mark some specific points but not the whole area. But also I can create an automatically generated mesh. So again, show mesh. I will enter how many points do I need, and here I can specify the type of triangulation. Let's put there random triangles, and also smooth them so they are all more of the same size. Well, let's review the results. Show the graph and select which values I want to plot. Then pick a time point and choose a value to be mapped. Also, I can use a local or a global color scale. Global takes in consideration all values in the measurement, while local sets the color scale limits only for values in each data point. Now I can playback the test in various speeds. But what if I need or want to see the strain distribution during the test, as it is not really possible with area probe for its high computational power requirements? For these cases, we implemented a strain distribution feature that is line-based, so it keeps a high sampling frequency during the test while providing a 1D strain mapping feature. It is basically a line section of DIC area probe. Now to the way how we get these results. It all starts with a well-performed calibration to which the measurement methods are linked. Some methods can have output to a testing machine or data acquisition systems, and others are meant to be used to record the data for post-process analysis. But it all starts with a calibration. One of the main reasons of calibrating the DIC system is to compensate the optical distortions that are unique for every camera lens. Typically, it is barrel distortion, and as you can see, if we would not compensate it, a rigid body movement from the center of the image would be determined as a negative strain. Another reasons for calibrations are settings of the calibration plane in space, and last but not least, the determination of the ratio between the pixel and the chosen physical unit. Now, how the calibration is done? Let's create a new one. Set the calibration name, turn on the lights and select the camera we would like to use. Now, let's consider we are using a wedge grips in this video. I will put my calibration grid into the machine, and because I know that we are using a 3 mm thick calibration plate, I will enter half of it because it is the distance between the axis and the grid surface. I will detect, and now I will create a second calibration point in some known distance. So I will insert a plate of a known thickness. Now I'm gonna use a 2 mm, and I will enter this 3 mm of a grid and the half of the plate. So I will enter 4 mm. So 4 mm. I will press the grid against the plate. Now detect again, and that's it. In this overview, we can see that the calibration covers a range between 1.5 and 4 mm distance between the machine axis and the measurement plane. And because the calibration function is a linear function, we can interpolate a scale factor for any specimen thickness or diameter inside the calibrated range. We can also extrapolate the scale factor, but only up to a certain extent to avoid a possible bias. So I hope you have enjoyed the video and it has been meaningful for you. Here I would like to thank all of you for the attention and also invite you to our website where you can check more information or videos.